Yeah, so I'll be talking about our efforts in automation, high throughput experimentation, and incorporation of artificial intelligence to develop self-driving labs. So this title is Sustainable Material Acceleration Platforms. These are platforms that accelerate the development of materials for thin film research in perovskite photovoltaics. And so I'm very pleased to be speaking to this audience about our efforts from North Carolina State University in the United States. So we're very interested in tandem applications and developing materials for tandems. And metal halide perovskites have this remarkable tunability as well as fantastic properties: the absorption, the direct band gap, the mobility, the carrier lifetime. And if we can solve the stability problems, then of course we can address the problem, the opportunity of low-cost tandems, whether they're hybrid tandems, whether they are all perovskite tandems. I think this is a tremendous opportunity for the future. And in this context, the materials that are needed for the various technology, thin film photovoltaic and silicon-based technology nodes, there are already existing materials that could potentially address this in different device architectures. And that comes from the fact that we have a significant tunability of the band gap of the materials thanks to the halide composition tuning and some cation tuning as well that's available to us. But unfortunately, the story is not that simple. The problem is that the existing alloys and alloys in general, based on perovskites, appear to be more vulnerable than the unary pure compounds that we have. So one example is something that actually Mike McGee demonstrated, which is this light-induced halide segregation, where you expose the perovskite, mixed halide perovskite to light, and over time you will see that there's a segregation of the halide, and this leads to can lead to a failure of the material, but generally it also leads to temporary problems as well. Now, this problem can be addressed. At least there are solutions to this. I call them band-aid solutions. There's compositional fine-tuning that has been proposed. You could change the cation, you can do certain things, and you could really reduce the time over which this happens. There are passivation, and so there's been significant progress in the field in doing this. But I consider this a band-aid solution, and there is, in my view, and in the view of other people, there is really an opportunity to use alloy engineering to solve this problem and other problems of stability in perovskites. And I think it's sort of good to zoom out and look at what is the opportunity here. If we look at the number of cations we have, the number of halides we have, and the number of divalent metals we have available to us for the ABX3 structure, and we just do some calculations, the possible number of compounds or the phase diagrams to evaluate is absolutely enormous. And this number here is trillion, can be reduced down to, let's say, 1 million phase diagrams that we would have to evaluate if we just select, let's say, 2 halides just for lead. And that gives you an idea of the combinatorial explosion. And we have simply looked at thousands of those amongst the millions that are, or billions and trillions that are available to us. So if we just look at for every single metal, how many phase diagrams are out there? This is an important concept in materials that was critical for the development of steel and other important metal alloys and ceramics. It's not something we do right now in perovskites, but it's something we have to do in order to discover the new alloys that are going to be ultra stable, high performing materials. There are literally thousands and millions of these phase diagrams and maps that we have to screen and search through to discover these alloys. And you get into this space of high entropy perovskites as well, which is very, very interesting, that our peers in aerospace are looking at, for example, for completely different applications. So, a ternary here, this is what a ternary phase diagram looks like. In our community is already looking at these, but